Hi everyone and welcome back to my channel. Today we would be diving back into the Matlab world and we would be talking about the same differential equation and the kind of analysis that we were doing in the last lecture. So if you haven't watched it already, I highly recommend you to go and have a look at the last lecture and see the differential equation, the boundary conditions, and how we were actually supposed to solve that. So in the last lecture, I told you theoretically on the paper how the differential equation is actually solved, and today we would be doing the same thing in Matlab. And there would be a small announcement at the end of this video, so I highly appreciate if you can stick towards the end and look into that. So let's jump right into the Matlab now. So before I go over to the Matlab, I would briefly re-summarize whatever we were doing in the last lecture. So this was our differential equation, d square y over dx square being 0. The boundary conditions was that the variable, this should be y. So the y variable, so I'll just write y, should be 0 at the left boundary and it should be 1 at the right boundary. And we saw that the discretized version of this governing equation becomes that yi is the average of yi minus 1 and yi plus 1. And we were supposed to write a code for that. So as I told you, we can take a small domain, let's say 5 points, just for the sake of understanding here. And first, we have to define the problem. So we have to define in the code how many points are there. That would also define our grid spacing. Then we force the boundary conditions and the initial conditions of the problem. So I'll show you in Matlab how we write about this. So this is the Matlab interface here. Just like previously, I have my current working folder on the left. I have a workspace on the right in which I have already solved the problem that contains some variables. My command window is here on the top, while my editor is here on the bottom. My first section clears all the variable, closes all the figure and cleans the command window. So I hit Control Enter and you see that all the variables are gone. So I start with a fresh code. So the first part or the first step is to define the problem, and we define how many points are there. So in the Matlab, I say that the number of points are 5 and I put a semicolon at the end so that it doesn't get displayed. The second one is the domain size. So typically in fluid dynamics problem or any kind of computational problems, the domain is always treated as unity. So that's also one way to normalize the domain size. So in this case, we have set the domain size is 1. And finally, the grid spacing h, it is the domain size divided by total number of points minus 1. This minus 1 is important because, so this is where these small figures come in very handy. So you know that there are 5 points here, but the domain size is actually 1 by 4 because there are 4 parts or 4 partitions. So that's our domain size. So if I hit Control Enter, that's the code runs only this particular yellow section. And we've got the domain size, we've got the h, which is 1 by 4, and the total number of points being 5. The second part of the definition is we initialize the problem and we put the boundary conditions. So if you remember, the boundary conditions are y at 1 is 0 and y at 5 is 1. And the other points are 0 to be initialized as. So I do exactly that. I say that the y at 1 is 0. And because the code should be general, you should never hard code anything in the code and try to make it as general as possible. So I put y at n points, which in this case would be 5. So this indicates the last point in the problem, and that is being 1. And because we would be doing an iterative procedure, which would involve calculating a new value of y in every step, therefore I define 2 variables. One is called as y and one is called as y new, in which the new value would be saved. So I put the same boundary conditions on y new, which is y new of 1 is 0 and y new of n points is 1. And the cool thing about Matlab is, so I defined this variable say this is y1 and this is y5. And when I define y5, it automatically assumes that all the points in between or all the points before the defined variable or defined index here is automatically 0. So I don't need to write a code or write a line of code that says y2, y3, y4 being 0. When I define y5 equal to 1, it automatically understands that everything else before that is 0. So that happens for both y and y new. The second part here is we use the governing equation, but before that I would talk about error. So we said that we would define error to be the summation of differencing of the new value and the old value, and the calculations would stop once this error is less than a threshold value or a tolerance value. So in this case, I defined this tolerance value as error required. So I said that when the error is smaller than 1e minus 6 or 10 to the power minus 6, the problem I should actually define as minus 7. So the calculations would stop when the error is less than 10 to the power minus 6. And I'm defining these two variables, that is error magnitude, which would calculate this e, that is error magnitude, and the tolerance is 10 to the power minus 6, called as error required. And I'm finally defining another variable called iterations, just to give you an idea of how many iterations would it take for the code to converge or to get to that error value. So moving on to the part 2 here. So this says that we have to use the discretized form of the governing equations, which is the new value of y is the average of the old value of the neighboring values. So y2 at the new value of y2 is the average of y3 and y1, where these are the old values. So now we want to install this in the code. So one thing to note here is that the boundary conditions remain the same. So we don't have to use the governing equations on the boundary. We only have to use the governing equation from the point 2 to the second last point. So this is done using a for loop. This is very common in C programming or Matlab programming or even Fortran, that when you want to do these kind of repeated calculations for multiple points, you use a for loop that does for every single point. But we have a small conditions on using this for loop, which is that only use the for loop or only do these calculations when your error is larger than the tolerance value or the required error. So for that, I use what is called as a while loop. So I say that while the magnitude of error is larger than the required value of error. So as long as the error is larger than the required value, do the calculations, otherwise you stop it. So that is why the first sentence in my calculations is, while the error is larger than the required value, do these calculations. And if that is not, the code would end the calculation. So the while and the end, they are connected to each other. And similarly, the for is also connected with one end. So we would be talking about that now. So as you see here, so I'm saying that for I, so I is just an index that is used to refer to these points here. So I would take the value of 2 at first, then I would take a value of 3, and then I would take a value of 4. So the way in which Matlab does is, so we say that for I being 2, and then you remember here the 4 is n points, which is 5 minus 1. So I'm saying that for I equals to 2, and then there is a ratio sign which indicates that after 2 you take 1 off. So from 2 then you go 3, 4, 5, 6, and the second entry, that is n points minus 1, that represents until when you have to do this increment. So I said for I being 2 to n points minus 1, that is 4. So do that from 2, 3 and 4. So you have got 3 points on which the for loop would be executed. Then I said that use the for loop for these points, and what you need to do is you say that the y new at I. So you remember how this I is coming into the picture? This is the same I that we use in all the equations and the discretized form of those equations. So we say that the new value of I is half of 0.5. This is the sign of multiplication, while the point means, this dot means that it's multiplied to every element. So this line is equivalent to 0.5 times yi minus 1 plus 0.5 times yi plus 1. This code would still work if you don't have this dot sign, but as I'll be showing you later, this dot sign is very useful when you have multiple elements in your matrix or your vector, and you want to multiply some quantity to every element, or you want to multiply one matrix by another matrix, then this dot symbol becomes very important. So once we do this, this is the key line of our code. I say that iterations equal to iterations plus 1, because after executing this particular line of command, it means that we have performed one iteration. So I made that iterations equal to iterations plus 1. So that's the part where we solve the governing equation. Now we want to see whether we have actually converged the solution or not. And for that, we need to calculate the error. And remember, the error is the old value minus the new value and the magnitude of that and its summation over the entire domain. So we reinitialize this magnitude of error equal to 0 because we want to start with a 0, and then what we do is we use a for loop for all the points inside the domain because the boundary conditions stay the same. And we say that for all the interior points, that is I equals to 2 to n points minus 1, error mag, which we initialized at 0 here, error mag is error mag plus absolute, because we want the absolute value of yi minus y new I. So the way the summation is done over all the domain is, suppose you for I equals to 2, this particular absolute value is 1. And then if you want to go to the next point, you want to retain this 1 plus this number. So that is why it's called error equal to error plus the new value. Then again, this is taken over to the other value. This is, in C programming, this is called as recursive functions or recursive programming. And you can do it in multiple ways, but this is the way I have been typically doing it over the years, and it always works. There is no doubt that it wouldn't work for you. And once we calculate that, we get this particular total summation, that is E. So this defines your error magnitude. And finally, what I do is, once we have done the calculations, we have to make sure that to repeat the calculations, the new values are allocated back to the old values so that the new iteration would use these values that we have just obtained. So that is why the y is y new. So again, the code would look for whether the magnitude of error is less than the required error. If that is not less than the required error, then it would do the calculations again. And just one small thing to be mentioned here is the reason why I defined this error magnitude to be 1 at the start is just because so that the first iteration can happen. If I define it 0 here, then this particular statement, it would be false, and the code would understand that the solution is already converged. So initially I have to define it to be larger than required error if I have to proceed this way. And once the code goes into this statement or inside the loop here, then we re-initialize it at 0 so that the code doesn't confuse it with this 1 here. So this particular 1 definition is only for the first loop, just so that we can get into the calculations. And finally, so I'll use Control Enter on the initialized problem. So you see all my variables have been initialized here. And finally, when we come at the calculations, and if I hit Control Enter, you see that the code takes 138 iterations to come to the converged solution, and the final magnitude of the error is 5 into 10 to the power minus 8, and which is smaller than the tolerance that we asked for. And another thing that you can try is you can change this required error magnitude, and you can see how the iterations that you need to achieve to that error would change. So this means that we have got the converged solution, and the final piece of puzzle in any kind of CFD problem is to visualize the data and see how the data is looking. So we saw in this case that this is nothing but a simple straight line with 0 at one end and 1 at the another. So to visualize the data, what I'm doing here is, because we need the x coordinate for the domain here, so we know that this is 0, this is 1, and I know the grid spacing. So every point here is just one grid spacing apart, and therefore the x domain or the x location of the domain becomes, so I say 1, and then the ratio sign which indicates that I'm giving a spacing of unit. So 1, 2, 3, 4, 5 until the end points. Then I'm subtracting 1 because my first point is supposed to be starting from, or the x location of the first point is 0. So the x of 1 is 0. So that is why 1 endpoints minus 1. And then I'm using again this dot sign so that every element in that vector, it gets multiplied by the grid spacing, which is h. So while I do that, I'll first only take this part. I'm not including this semicolon. I want to see what the x domain is in the command window. I right click and I evaluate selection. And that gives the x domain is 0, 0.25, 0.5, 0.75 and 1, which is exactly what we want. That is 0, 0.25, 0.5, 0.75 and 1. And once that is done, we open a figure using figure exclamation semicolon, evaluate selection, that opens a figure, and then we use what is called as a plot command. So the two variables in the plot command are that the first thing is what you want on the x-axis, which is x domain or x term, and y. So x term would be plotted on the x-axis and y would be plotted on y-axis. So the y here is the converged solution of this calculation loop. So if I use this, right click, or you can also press F9 and use evaluate selection and go back to the plot. My fault, I think I mistakenly cut that. So again, evaluate selection, go back to the plot, and you see we have a straight line that starts from 0, 0, and it goes to 1, 1. And we can do many things about the plot, but we would be looking at all these details later. The point here is to get an idea of how you can obtain a basic plot after you have completed all the calculations. So I hope that you get an idea of how to write a very basic iterative code. So to give you a summary of what we have learned today, so we first initialize the problem. We initialize both the old variable and a new variable, just so that we can keep the coding nice and clean. If you want, you can still use the old variable, but I feel that that creates a mess sometimes. So it's very good if you have one set of old variables and one set of new variables. The second part is we defined the error and we told the code until the error is smaller than what we want, keep doing the coding or keep doing the solution procedure. So for that, we used a while loop. This could also be achieved using a if loop. As is always with the coding, there are more than one ways to achieve to that solution. So it's totally up to you. In this case, we have used a while loop. Then for the repetitive or the iterative process, we use a for loop on every point, and that contains the discretized form of the governing equation. And after obtaining that solution, we calculated what the error is, and then we saw or we compared whether that error is smaller than the magnitude of error that we want or not. And once that is smaller than that, we call that a day and we look at the solution. The final thing that I want to, this is totally on a different note, I'm going to start a very fundamental course on fluid mechanics, and that won't be on YouTube. It would be available on an app, and I'll provide the link in the description. That would be covering very basic fluid mechanics. So if you are not very familiar with fluid mechanics, which I'm sure you would be at this point, but if you feel that you need a refresher or you need a course that would cover the fundamentals of fluid mechanics of all these governing equations, then I think that would be super beneficial to you. And if you know someone who might be struggling as of now with fluid mechanics especially, I highly recommend that you share the link with them so that they could have a look and benefited from them. So that would be all for this lecture, and in the next lecture we would be diving a little bit deeper into the domain of the CFD, and we would see how we can jump from 1D problems to 2D problems. So hopefully you can catch up on all the materials so far, and if you have any questions, feel free to ask them in the comments, and I'll definitely try my best to answer them ASAP. And if you haven't already, please subscribe to my channel so that you can get the updates for the upcoming videos. Stay safe, and I'll see you in the next one.